Good afternoon. Before I introduce the winners and present the results, let me congratulate and thank all the participants. It was your enthusiasm and contributions that made this challenge a success. So, the outline of my talk is basically I have a slide on participation, which Adam talked about a little. I will describe the meta-big data set and the impact of the clinical variables in relation to the chosen endpoints, because we had two endpoints. How the challenge evolved, an overview of the predictions, which samples are easier and harder to predict, meta-analysis of predictions, which was one of the questions addressed earlier. I will also talk about overfitting, which was another question, and then present the winners. So, as Adam said, we had 3 phases. In the first phase, we had about 37 participants that successfully submitted models. The number of actual registered participants was in the hundreds. But when you trim that by the number of the ones that submitted a successful model, then you go down to 37. And they managed to submit together in the first phase about 900 models that were also successfully evaluated on our servers. A lot of models failed, so I'm not counting those, but they failed because of software errors and participants had to ask questions and then resubmit and so on. In the second phase, we had more participants that submitted even more models. So between the 2 phases, we had almost 2,000 successful models that were evaluated on our servers. And in the end, everyone had to choose 5 models to submit for final evaluation, which was done on a separate data set, not the one used for the leaderboard. So this is the meta-big data set. It consists of roughly 2,000 breast cancer samples that were in this case, the ER-positive one and lymph node negative ones did not receive chemotherapy. These are pretty old samples, and the standard of care changed in the meantime. But this was back then. Most of them got also hormonal therapies if they were ER-positive. ER-negative, lymph node positive ones did receive chemo, and none of the HER2-positive ones received targeted therapy with Herceptin. This was before this became the standard of care for HER2-positive patients. The median age of diagnosis is about 62 years. About half of them are lymph node negative, so this is pretty balanced. And 3/4 are ER-positive. And we'll see how this actually impacted the result. 3/4 is just about right for mirroring the actual percentage level of ER-positive in a breast cancer population. So as I said, we had 2 endpoints. We didn't have time to distance metastasis, but we had overall survival and disease-specific survival. Now, disease-specific survival is hard to define because, as you know, nobody dies of cancer per se. It died of other complications. But still, the curators of this data set did a pretty good job of filtering out, I guess, obvious non-disease-specific events like a car accident, I guess. So in this case, this is a multivariate Cox analysis of the clinical variables. And age is obviously the most significant for overall survival. And this significance decreases when you look at disease-specific survival. Because in this case, you get molecular markers that are more significant, like grade. So this shows us that if we want to have better results with this kind of challenge, we need something that's more disease-specific, like time to distant metastasis. The problem is that FDA prefers overall survival because this makes it easier for different trials to be compared between them. And in the end, that's your goal, to increase survival. So we didn't use this specific survival. We just used overall survival. Also because the final cohort, the Norwegian cohort that will be the last phase of this challenge, has overall survival as an endpoint. And obviously here, you see the treatments are all very significant because that matters. You have combinations of chemotherapy with hormonal therapy. You have chemo, hormonal, and radiotherapy. You have no treatment at all. You have radiotherapy alone, and so on. In order to judge the models, we used a measure called Concordance Index, which just counts the fraction of all pairs of subjects whose predicted survival times are correctly ordered. So basically, you need to order them right. Is the order that matters. So you can use any risk predictor you want, as long as you get the order right. So this is related to area under the curve, ROC curve, and the Mann-Whitney statistic. And this is the formula. It's very simple. First phase, we didn't have the raw data yet. So we used the normalized data from Metabrick. The problem with that normalization is that the training set had no missing values. They were all in the test set. So we didn't use any missing value information here. It has some batch effect based on site. And not all the clinical variables were included at this point, because we weren't sure which one will be present in the Norwegian cohort. This is the evolution of the best performer. Every time on the leaderboard, every time you see a color change, there's a change in the leader. So just remember, the orange one is our final winner, which I'll present in the end. And the baseline one was at 0.69, which was a simple Cox regression on clinical variables alone. So as you see in time, we get a decent improvement by using the molecular data as well. So up to over 0.74. In the second phase of the challenge, we finally got the raw Metabrick data, and we renormalized it and in order for it to be comparable with our final cohort, the Norwegian cohort. And we kept 1,000 for training. 500 were used for the leaderboard, and 480 were used for the final evaluation of models. So in this final evaluation, only 5 models per team were scored. This time we had missing values, so people had to deal with that. The site-based effects were corrected, and we used overall survival as an endpoint. In the phase 1, we used disease-specific survival, and as you see here, the scores are a little bit lower because of the overall survival issue. The baseline is somewhere between 0.68 and 0.69, and it was a random forest regression with a few selected genes from the literature. And still participants improved with time a lot on this score. This is an overview of the ranks predicted by all the participants. So on the x-axis, we have the patients sorted by survival, and on the y-axis, it's the average predicted rank. So on the top graph is the average predicted rank among all participants. And as you see, the trend line is pretty good, consistent with the rank of the actual ranks, but you have a lot of noise. The slope of this trend line is improved if you just look at the top 5 teams, but there's still a lot of noise. So which were the samples that were predicted better and which were predicted worse? So if we look at the patients with an early event, up to 4 years, then 4 to 8 years, and then 8+. You see that the early event ones are the hardest to predict. So basically, this says that aggressive cancers are harder to order. Why? Well, if we look at the classic breast cancer markers, you see that the ER negative and triple negative cancers, which are also the more aggressive ones, are also harder to predict. And this correlates with my previous slide. Fortunately, people did pretty well at predicting ER positive cancers. And that's a good thing because that's 75% of the data. So you need to do well on this. If we looked at, when we looked at just ER negative or just triple negative, which is a minority of the data, the scores are lower, but also the ranking is different. How about grades? So this is interesting. Intermediate grade is easier to predict. I don't know how to explain this. Maybe the extremes are harder to predict. And you have more granularity in the middle. We also combined the predictions to see if we do any better. So in blue are the individual scores ranked by their performance. And in red, we plotted the consensus scores for top teams. So we don't do better than the top performing team when we do consensus scoring, consensus methods. But even when we add the poor performing models, the score is robust. So one of the reasons why adding all the models together doesn't do better than the top model is that the top models are meta models themselves. So we are combining combinations. So that obviously will not work. A way to look at this is a way to look at how correlated the predictions are. So we looked at the PCA plot of a matrix of predicted ranks for all teams. So as you see, there are two clusters. There's a big cluster where the winning model is, and there's a smaller cluster. So the smaller cluster has all poor performing models. And the big cluster has all the better performing models. The problem is they are very correlated because this was an open challenge, and at some point people started using a lot of the best performing code. So maybe open challenges are good, that they in taking one idea and improving it, but not good at creating diversity of ideas. So we will have to think better at incentivizing these kind of challenges. One idea is to only allow people to see the code if you're doing better than that team. So if you want to see the code for the best performing team, you better do better than them. That's my idea. This is how people would do if they collaborated. This is just the top 10 teams, and these are the pairwise scores. So the top one in the left corner is the best team. And as you see, it doesn't help them if they collaborate with the immediate next ranks. They have to go even lower. Because some teams did better at predicting, let's say, triple negatives, but overall they will not do well. But they're good at predicting that. So maybe that's the one you want to collaborate with. So maybe in the future, we have to add different columns in our leaderboard saying that this is the score for triple negative, this is the score for ER positive, and so on. So overfitting didn't happen that much, surprisingly, considering we had 2,000 models. But then again, the test set is 500, so that's a pretty big number. 500 factorial is really big. So this is a scatter plot of the final test versus the initial test. So you see in the bottom, there is some overfitting, but they're pretty well correlated. If we look at the phase 2 evolution, in red, it's the corresponding score of each model for the final test. And there's also some overfitting here. If you look at the second one from the last, you see there's a big drop there in here, right? It's a big drop. But this one is still good. So another way of, okay, so this is also we looked at how conserved the rankings are between teams for on the initial test set and the final test set. And as you see here, the #1 ranked team is #1 in both test sets. But as you go down, the rankings change a lot. So this one here, from second, it goes to 6th. These are the top models. This is our winner. And this is their score on the initial test. And in green is on the final test. So you see there's very little overfitting that they did. And they're also the winner, so that's good. And as you go down, overfitting happens a lot more. So basically, in order to win, not only you need to have a good score, you need to be very careful not to overfit. So a few conclusions from this before I present the winners. Disease-specific endpoints are easier to predict, but they're harder to define. The ability to predict overall survival varies depending on breast cancer type and severity. There was little overfitting between initial and final validation. And the issue of open source challenges that we need to, maybe we will talk in the final discussion. And these are the best performing teams. #1 is Team Attractor Metagene. The team members, Wei Cheng, I'm going to misspell this, Tai Hsiengo Yang and Dimitris Anastasiou from Columbia University. And the second ranked team is Speed Transmed. Team members Chunhui Kan, Xinhu Lu from University of Pittsburgh.
Thanks, Erhan. So we're going to get the top performing team to come up. Oh, you want to do questions?
I have
Does
time.
anybody have any questions on scoring?
What kinds of index do you use to measure the performance of these models?
What kind of measure I used for? Yeah, so it's, as I presented in the beginning, it's called the Concordance Index. So it's a measure of how well one orders the samples.
So you need to compute the true positive rate and false positive rate first?
Not really. You take every 2 samples and you see if they are correctly ordered. And then you calculate the fraction of all these values. So you do it pairwise.
And the other questions, when you evaluate one models, do you consider the time consumption?
If we consider how long the model runs?
Yeah.
No, we didn't consider that.
Oh, okay. Thank you.
So something that I'm not sure that I understood, maybe it's a naive question, but so the concordance is based on the actual data that you know. So this is like a longitudinal study, you know how long these people
Yeah, we have the survival.
survived. So do you have also the data in what was the clinician prognosis at the time of the diagnosis?
No, we don't have that data.
So at that time, the patients probably they were told something, right? When they had said, no, you have breast cancer, and
I don't think that kind of information is recorded. I've never seen it. They do see, they get grade information and stage, which tells them pretty much how long they have.
Right. I guess, no.
It's an interesting question, but I have never seen it. I've never seen that data recorded.
Or quick question?
Yeah, you said so the prediction for the Concordance Index based just on the clinical data was 0.68.
Mm-hmm.
And then when you bring to bear all the molecular data, you boosted by only 6% to 0.74.
Yes.
Was that a little disappointing or unexpected?
While working on this challenge, we found that increasing just by 1% is extremely difficult. And when you're looking at the big population, a few percentage is still significant, and that can give you also some features that might be useful. And I expect that you will never be able to predict 100%. So there's an inherent limit to that as well. If we had time to distance metastasis, there's an indication from the disease-specific endpoint that we had that that difference will be a bit bigger. Yeah.
Yep. Okay.